Hi, I'm Mark Barsamian. In this video, I'll be discussing limits involving infinity. This material is in the Barnett book, section 2.2. In this video, I'm going to consider a graphical approach to limits involving infinity. Let me start with a definition of infinite limits. I'll start with a symbol. This is spoken, the limit as x approaches c of f of x is infinity. Now, I will tell you what this means in just a second, but first let me tell you the usage of this. That is, let me tell you what the various parts of this symbol are. X is a variable, f is a function, and c is a real number constant. Now, what does this symbol mean? It means the following. As x gets closer and closer to c, but not equal to c, the values of f of x get more and more positive without bound. Now, what is the graphical significance of this? Well, I'll skip that and I'll start by drawing a picture of this kind of situation. Here's an example of a graph that has this kind of behavior. Now let's notice on this graph, if I choose an x value close to c but not equal to c, I get a large positive y value. And notice that if I choose an x even closer to c, I get an even larger positive y value. So that's how a graph would look. The way we describe this behavior is we say that the graph of f of x has a vertical asymptote at x equals c. And in fact, the line equation for that asymptote is the equation x equals c. And I should say a little bit more. Not only do we have a vertical asymptote, the graph is going up along the asymptote on both sides. So that's the definition of infinite limit and a picture of an example. What is the significance of the phrase without bound in this definition? Well, consider these two graphs. So on the left, I have a graph that I'm going to call f of x, and notice that as x approaches 3 on the graph of f of x, the y values are getting more and more positive. But on the graph on the left, the y values are getting more and more positive and approaching 7. So in fact, we would say that the limit as x approaches 3 of f of x is 7. Because the graph is heading for the location 3, 7. But on the graph on the right, the y values are getting more and more positive, but without bound. So as x gets closer and closer to 3, the y values get more and more positive without bound. So in this graph, if I choose an x value even closer to 3, so for instance this green one, its y value will be huge and positive. Now, important thing to notice is that for the drawing above, there's a typo here. This should say G. So in section 2.1, we would say that the limit as x approaches 3 of g of x does not exist. But in section 2.2, we say the limit does exist, and it's infinity. Now, the book says some confusing stuff. They use this symbol to describe the behavior of the graph of g of x, but in words, they still say that the limit does not exist. I find that very confusing, and it's not really capturing the spirit of what we are doing. We are revising the definition of limit. We're kind of enlarging the kinds of things that we can describe using the terminology and notation of limits. So in section 2.1, we had pictures like this, and limits were always numbers. And in section 2.2, we can still have pictures like that, but we also are going to have pictures like this, where the limits can be infinite. All right, there are obvious variations on this kind of terminology. First of all, what I would call a one-sided limit. That is, the limit as x approaches c from the right of f of x is infinity. What would that mean? Well, it would mean the obvious thing. As x gets closer and closer to c, but greater than c, the values of f of x get more and more positive without bound. And a picture of that would be a vertical asymptote with the graph going up along the right side of the asymptote. So in other words, this symbol tells us we have a vertical asymptote, but it only tells us what's going on the right side of that asymptote. Another fairly obvious generalization of the idea of infinite limit is the following. This symbol here is spoken, the limit as x approaches c of f of x is negative infinity. And its meaning is obvious. As x approaches c, the values of f of x get more and more negative without bound. So a picture of this would be a vertical asymptote with the equation x equals c, and the graph of f of x going down along both sides of that asymptote. So an observation. With the definition of infinite limits, we now have a shorthand notation to describe situations where the y values of a function are getting more and more positive or negative without bound. Another kind of limit involving infinity is what is referred to as limits at infinity. The first kind that I will introduce is denoted by this symbol. This is spoken, the limit as x goes to infinity of f of x is b. Now, what's the usage in this symbol? That is, what are the parts of this symbol? Well, x is a variable, f is a function, and b is a real number constant. What does it mean? It means that as x gets more and more positive without bound, the values of f of x get closer and closer to b, and may actually equal b. Well, what does this mean in terms of a graph? I'll start by drawing a picture. All right, notice in this picture, when I choose a large positive x value, like that one, and look at its y value, the y value comes out close to b. And if I choose a larger and larger positive x value, so for instance, x values maybe out here, then the y values come out even closer to b. So x values getting more and more positive without bound cause the y values to get closer and closer to b. And they may even equal b. So let me draw another picture of a graph that has that limit behavior. So in this graph, notice that the y values, as I go off the right end of the graph, the y values are getting closer and closer to b, or they're remaining closer and closer to b, and sometimes they actually are b. Sometimes they actually are equal to the number b. In other words, the graph crosses this dotted line over and over again. Each time it crosses, it remains a little bit closer to the dotted line. So that's what I mean by the y values may, in fact, even equal b. They don't have to stay equal to b, but they have to remain closer and closer to b. So this kind of behavior I would describe as a horizontal asymptote. So I would say that the graph of f or g has a horizontal asymptote, and I should say that the asymptote is on the right. So the graphical significance is the graph has a horizontal asymptote on the right, and we should say even more. We should give the equation of the asymptote. Remember, the form of the equation for a horizontal line is y equals b. There are obvious variations of this kind of idea as well. One is the limit at negative infinity. So that's denoted by this symbol. This is spoken, the limit as x goes to negative infinity of f of x is b. What does this mean? It means that as the values of x get more and more negative without bound, the values of f of x get closer and closer to the number b and may even equal b. So that's the meaning. Let me draw a picture of this kind of behavior. So there are two pictures of functions that have this kind of limit behavior, and we can see that we would call this an asymptote, a horizontal asymptote, on the left. So the graph of f or g has a horizontal asymptote with equation y equals b on the left. We can combine the idea of infinite limits and limits at infinity in the obvious way, using this symbol. This is spoken, the limit as x goes to infinity of f of x is infinity. And the meaning is what you would think. As x gets more and more positive without bound, the values of f of x get more and more positive without bound. A picture of a graph that does this would be, so you can see in a graph that behaves as described in this sentence, the right end of the graph goes up. So the graphical significance would be, so notice that the term limit at infinity or limit at negative infinity, it refers to what the right end of the graph is doing. This is called the end behavior. So in this green graph, the end behavior is the right end goes up, and that's encapsulated in this expression involving limits. this expression tells us that the right end of the graph goes up. For the rest of this video, I'm going to do examples of limits involving infinity for a function given by a graph. Here's the graph. Our first question is to find this limit. Now, this refers to the left end behavior of the function because x is going to negative infinity. So let's go up and look at the graph and see what the left end of the graph is doing. That's this. We can see that the graph, it has a horizontal asymptote on the left with line equation y equals 1. So that number, y equals 1, tells us that the value of this limit is 1. So our explanation is because the graph has a horizontal asymptote on the left with line equation y equals 1. Our next examples involve the same graph, but looking at a different part of the graph. Our next question, question B, is to find this limit. Now that refers to the part of the graph where x is getting closer and closer to negative 3, but not equal to negative 3. So let's look on the graph there. You can see that the graph of f has a vertical asymptote at x equals negative 3. So in sentence, we would say the graph has a vertical asymptote with line equation x equals negative 3, and the graph goes up along both sides of that asymptote. Or we could say, as x gets closer and closer to negative 3, but not equal to negative 3, the y values get more and more positive without bound. So the abbreviation for those sentences that I just spoke is this. We say that the limit is infinity, and we write this symbol. And so I'll write down, by way of explanation, I'll write down that sentence that I just said about the graph behavior. So as x approaches negative 3, the values of f of x get more and more positive without bound. And remember that I also spoke this in a different way using the shorthand notation of vertical asymptote, so maybe I'll write that as well. So the graph of f has a vertical asymptote with line equation x equals negative 3, and the graph goes up along both sides of the asymptote. Now question C is to find this. That symbol denotes the y value when x equals 3. So, well, that does not exist. And that's because there is no point on the graph when x equals 3. So the limit is infinity. The y value does not exist. Our next 4 questions have to do with behavior around x equals 1. Question D asks us to find this limit. Now that's the limit as x approaches 1 from the left. Notice the behavior. The graph of f has a vertical asymptote at x equals 1, and the graph goes up along the left side of that asymptote. So let me write that sentence down over here on the right. Now, remember that we have a shorthand notation and shorthand terminology for that behavior. We say that this limit is infinity. So that symbol and that sentence that I just spoke, the limit as x approaches 1 from the left of f of x is infinity, is just shorthand notation for this sentence that I wrote down in words. So you should be noticing by now that the word infinity and the symbol infinity is just shorthand terminology and notation. Now let's do this question, the limit as x approaches 1 from the right of f of x. Well, that refers to this part of the graph. X is getting closer and closer to 1, but to the right of 1. So let's notice what happens on the graph at that part in that part of the graph and describe it in the sentence. The graph has a vertical asymptote, again with line equation x equals 1, and the graph goes down along the right side of that asymptote. Now remember what terminology we use for that. We say that the limit is negative infinity. We write the symbol negative infinity symbol. So the infinity in this symbol refers to the graph going up or down. Now what about question F? Question F, we say that the limit does not exist because the left and right limits don't match. And finally, question G, f of 1, does not exist because there's no point on the graph at x equals 1. Now we have 4 questions having to do with the behavior of the graph around x equals 4. First, we start with this limit. That's limit from the left at x equals 4. So that refers to this portion of the graph. So notice we have a vertical asymptote with line equation x equals 4, and the graph goes down along that asymptote on the left side. So those words that I just spoke and wrote are abbreviated by the following symbol. I put negative infinity symbol. This is spoken. The limit as x approaches 4 from the left of f of x is negative infinity. All right, what about question I? The limit as x approaches 4 from the right. Well, that refers to behavior on the graph when x is getting closer and closer to 4, but greater than 4. That refers to that part of the graph. So you see that the graph is heading for the location 4, 1 from the right. So in this symbol, the x is 4 and y is 1 for that location that the graph is heading for. Well, those symbols show up over here in this limit expression. There's my 4, and I put the number 1 here. The limit as x approaches 4 from the right is the number 1. That's because the graph is heading for that location, 4, 1 from the right. Now, what about this expression? Well, this limit does not exist for the simple reason that the left and right limits don't match. And finally, question K, the value of f of 4 is the number 1. It's because there is a point on the graph at 4, 1. So notice that in this drawing around x equals 4, it sure looks like 4, 1 is an incredibly important point, and it is. That's the y value, y equals 1. But the limit does not exist. You might be tempted to say that the limit is 1 because that's where the dot is, but that doesn't matter. The limit refers to the idea of which location does it look like the graph is heading towards. Well, there is not a single location that the graph seems to be heading for. Part of the graph is heading down, and part of the graph is heading for that location. So we have to say that the limit does not exist. Finally, we ask, what is this limit? Now that refers to the right end of the graph. The right end of the graph goes up without bound. So the shorthand notation for that is that we put this symbol here. This is spoken, the limit as x goes to infinity of f of x is infinity. Now I'd like to summarize the limit terminology from sections 2.1 and 2.2. As I've said before, limit terminology is simply an abbreviation for different kinds of trends that can occur in x values and y values. And the corresponding limit notation is an even more condensed abbreviation. So here's a summary of the limit notation and corresponding trends. First of all, the limit notation introduced in section 2.1. Well, in section 2.1, the kinds of trends that we could observe in the x coordinates were x is approaching some number from the left or from the right. And the only kinds of trends that we could observe in the y coordinates were y values approaching some number, L. So in the case that those trends were observed, we had these kinds of symbols that denoted that. So for instance, this symbol means that when x is getting closer and closer to c from the right, that's a trend. The y values are getting closer and closer to the number L, that's a trend. A trend in the x value and a trend in the y value. In section 2.1, we didn't have any kind of terminology to describe any other kind of trend. Any other kind of trend in the x values, any other kind of trend in the y values. So if the x values did this stuff, but the y values did anything else but approach some number, then we would just have to say that the limit does not exist. And if the x values did anything but just simply approach some number, if the x values do anything else, then we didn't have any abbreviation for that situation. So in section 2.1, a limit could only be a real number occurring at a particular x value, and it denoted that the graph was heading for a location x, y equals c, comma, L. Now let's turn our attention to what we've discussed about section 2.2. In section 2.2, we enlarged our definition of limit to have abbreviations for more kinds of trends. So here are now the kinds of trends that we can look for in the x values. X's can approach numbers, or x values can grow positive or negative without bound. And the kinds of trends in the y values that we are looking for now are these things. We're looking for y values approaching a number L, or y values growing more and more positive without bound, or more and more negative without bound. So in this table, all of this shaded gray stuff is the stuff that we discussed in section 2.2. New terminology and new notation that are abbreviations for new kinds of trends, or trends that we did not have abbreviations for and notation for in section 2.1. So our idea of limit now is that we have abbreviations for all of these situations. Some of those abbreviations were discussed in section 2.1. Some of them were discussed in section 2.2. That's the end of the video. Thank you.